Welcome to this explainer. If you've ever wondered how a machine learning algorithm looks at just a massive chaotic pile of data and actually learns to make an accurate prediction from it, well, you are definitely in the right place. Today, we're going to be peeling back the mathematical layers of decision trees. And we're putting two heavyweight formulas right into the ring to duke it out: information gain and the Gini index.
Okay, let's dive into this and look at our structural roadmap. We'll be moving from basic concepts to a fascinating real-world application today. First up, how decision trees work. Second, the diabetes data example. Third, information gain and entropy. Fourth, the Gini index explained. Fifth, predicting rain in Kashmir. And finally, number 6, which method is better? Section 1, how decision trees work. Conceptually, you can really just think of a decision tree as playing a highly efficient game of 20 questions. Your whole goal is to ask the absolute best question that eliminates the most incorrect answers at every single step along the way. But here is the fascinating problem. When an algorithm is staring down thousands of data points and dozens of features, how exactly does it know which question to ask first? How does it mathematically guarantee the most effective split? Well, the answer lies in the pursuit of purity. A decision tree is a heuristic algorithm that recursively splits data partitions into smaller, purer classes. The ultimate goal here, to reach a point where every single record in a partition belongs to the exact same class. To get there, the algorithm relies on specific selection measures to mathematically score every possible split. All right, moving on to section 2, the diabetes data example. Let's look at splitting for purity in action. To really ground this, just imagine a data set of 100 people. Some have diabetes, some don't. We have two features we can use to split our data: gender and whether their fasting sugar level is above or below 120. Now the algorithm has to choose its starting point. Should it divide the group by gender first or by fasting sugar? Now, what's really interesting about this slide is the mathematical output of that choice. Splitting by fasting sugar reduces impurity by a massive 0.273. But splitting by gender? Only 0.0263. Fasting sugar is literally 10 times more effective at creating pure groups. The algorithm instantly knows fasting sugar is the superior choice. But how exactly did it calculate those exact numbers? Which brings us to section 3, information gain and entropy. Let's look at the math behind the ID3 and C4.5 algorithms. To really wrap your head around information gain, you first have to understand entropy. In information theory, entropy is essentially just a measure of chaos or uncertainty. Think of it like this: a bucket filled with 50 apples and 50 oranges. That has high entropy. It's completely mixed up. But a bucket of 100 apples, entropy is 0. The chaos is totally gone. And honestly, the algorithm's entire mission in life is just to drive entropy down to 0. So, information gain is simply the measurement of that reduction in chaos. It calculates the entropy before the split, subtracts the entropy after, and then just looks at the difference. By constantly chasing the highest information gain, the algorithm builds a highly efficient, compact decision tree using the absolute fewest possible tests. Next up, section 4, the Gini index explained. Let's talk about the CART algorithm. While ID3 and C4.5 rely on information gain, there is a major rival algorithm known as CART, and it uses the Gini index. The Gini index also measures impurity, but it specifically evaluates binary splits, calculating a weighted sum to find the minimum possible Gini score. It is a fundamentally different mathematical path. So you have to ask, does picking one over the other actually change the machine's final decision? Let's look at section 5, predicting rain in Kashmir. It's info gain versus Gini in the real world. Dealing with weather means you're dealing with continuous data, like temperature, rather than simple yes or no categories. The heavy lifting for the algorithm looks like this. First, sort all the unique continuous values. Second, find the exact midpoints between adjacent values. Third, run the impurity formulas on every single midpoint. And finally, pick the one with the lowest impurity to act as the threshold. Sounds exhausting, right? And this brilliantly illustrates the sheer scale of that task applied to actual data. What we're looking at is a cleaned weather dataset from the India Meteorological Department across 3 recording stations in Kashmir. Researchers compiled nearly 6,000 records tracking temperature, rainfall, and humidity between 2012 and 2017. They literally forced both information gain and the Gini index to comb through thousands of midpoints just to figure out the best way to predict rain. So, Section 6. Which method is better? Let's compare the results of this Kashmir study.
The results were incredibly surprising. For minimum temperature and 12 a.m. humidity, the math actually corroborated perfectly. But when it came to maximum temperature, the formulas absolutely went to war. Information gain determined the optimal split was 25.5 degrees, but the Gini index, looking at the exact same data, said no, it's 8.05 degrees. You can see it right here in the direct dataset calculations. Out of 379 possible split points for maximum temperature, information gain favored row 286, which gives us that 25.05 degree threshold. The Gini index favored a completely different midpoint of 8.05 degrees. Guys, this wasn't just some minor rounding error. It was a massive structural disagreement that actually forced data scientists to manually step in and choose a winner to build their predictive model.
Which leaves us with this really vital takeaway. We so often treat machine learning algorithms as flawless, objective arbiters of truth. But as this weather data proves, the subtle choice of a core mathematical formula by a single developer can literally rewrite the branches of a decision tree. From medical diagnoses to automated loan approvals, how might these hidden mathematical choices be invisibly shaping the automated decisions that impact your daily life? Thanks so much for joining me for this explainer.